Hi, everybody. I'm Edward. I've been working for the last year and a half, probably even a little bit more than that, on the Aries project. This project actually started out when I came on board at Tlon and I was assigned to make aims faster. I fixed one bug in var that was some C code where we were looping over a gigantic array and individually zeroing some things, and it would show up when you had just booted a ship. And then I started looking at the profiler again, what else can we do to make this fast? And I realized that literally just calling arms in knock was going slow. And I said, what can we do to fix that? And it kind of spiraled from there. So, but what is the Aries project actually? Well, we should start with talking about what is Urbit, because Aries is all about Urbit, and Urbit is boiling the personal computing ocean. You come to assembly, you hear a lot about personal servers, and the personal server thing is a great, big piece of the use case for Urbit, but I tend to, in personal conversation, I'll tell people I don't think it's ambitious enough. If you go read the really old blog posts about Urbit, it doesn't talk about personal servers, it talks about personal computers. There's a whole bunch of things that we need from a personal computer, from the infrastructure from a personal computer, that Urbit can deliver. But how can it deliver it? Well, a lot of that right now is limited by the limitations of Urbit's runtime. So if Urbit is boiling the personal computing ocean, and Urbit runs on var, well, are there any alternatives? Are there any other approaches we can take? Well, there's another project that's called CL Urbit. It's by a guy who's happy as Fod White Ragful. And I asked him before this, I said, have you ever booted a LiveNet ship on CL Urbit? Have you ever, was that ever the goal for the project? And he said, no, it's just an experimental platform. Okay, well, are there any other things that we could try, any other efforts besides var? Well, there was one in Java called Jock, also by Fod White Ragful. Once again, I asked, well, this one's actually defunct, he said. And then I asked him, well, there's one more. It's called Truffle Knock. It's also written in Java. And he said, no, I haven't done that one either. And it's also by the same guy. So really, there's only one other person who's been, in his case, brave enough, in my case, foolhardy enough, I guess, to try to boil this ocean under the Urbit ocean. And that's what we aim to do with Aries. We're trying to boil the runtime ocean. What does it take to build a new runtime that supports the personal computer use case? Well, to answer that question, we got to talk about what does a runtime actually do? Well, it runs knock, right? You run knock, you can run Urbit, right? Well, first you actually have to say, okay, well, nouns are very abstract. A noun is an atom or a cell. However you can figure out, you can write the nouns down on paper, right? And that will take, if you try to boot Arvo on paper, it might take a very long time. But you need to lower nouns to some kind of abstraction that your computer understands, which mostly boils down to laying them out in your computer's memory. So you need to do memory allocation. You do actually need to run knock. That is an important part of what an Urbit runtime does. You need some jets. If you try to run your Urbit without any jets, you will eventually just start, very quickly you'll start just spinning in a loop in the code for decrement, and eventually you'll look at the star that our planet orbits around and notice that it's starting to get very red and very big, and you're not done running deck yet. You need some kind of persistent store. You want to be able to shut your Urbit off, walk away from it, come back to it later, turn it back on, and pick up where you left off. That's a key part of the story for Urbit, but that means that you actually need to be able to deliver really robust persistence. And you need to be able to talk to Earth. So memory allocation, again, like I said, lowers the abstraction level of nouns down to something your computer understands. What var does here combines the persistence and the memory allocation stories. They are two layers, but they're very tightly connected. If you talk about the loom and how Urbit has a 2 gig loom and now it has a 4 gig loom, this is the layer that we're talking about here. And the difficulty here is that for most of your nouns, you actually have to do a search for some free space. There are some optimized cases for cells because we allocate a lot of cells, but you actually have to do a search for your free space. So one of the ideas that I brought in to Aries was I said, what if we did the simplest, fastest memory allocation possible? I need 24 bytes for a cell. Let me move a pointer over by 24 bytes. Okay, then part of memory allocation is actually getting rid of memory when you're done. And when do you do that? So in var, you use reference counting and it's manual. Every time that you're done with a pointer to a noun, you actually have to lower a counter by 1 and then check if it's 0, and if so, kick off freeing all the memory. Well, we allocate a lot of nouns running Urbit, and most of them don't stick around very long. So what if we had a system where when we're done, we just check which nouns we still need. We just start with the noun we're returning, trace it, follow it back. And that's what Aries does. This is the stack allocator in Aries. So this is one of the layers that we had to build. This was one of the first things that we built. It exists, it runs, it works. You will see knock running on top of this here in a few minutes. Which is to say, once you can do this, once you can lay nouns out in memory, now you need to run knock. This has been a large part of my personal time. There's several contributors to the project. I see Alex in here. I can't really see more than a few rows back, so I'm sure some of the other people are in here. This has been, probably in terms of my individual dev time, the thing I've spent the most time on. Remember I mentioned at the beginning that this was the bug that bit me about the runtime in the beginning, that it takes a long time for one arm to call another arm when you're running knock right now. The primary reason for that is until you get there, you don't actually know what knock you're going to run. If you're familiar with programming at all, if you think about JavaScript, in JavaScript you can name some functions and then you can call them, which means that a JavaScript implementation can look at that name and say, okay, this function names that function's over here, we can just go run that function. In Urbit, it's not like that. It's closer to, in JavaScript, what we call eval, where instead you pass it, in JavaScript, you pass eval a string that is compiled to some JavaScript, and then you run it. So in Urbit, we don't ever call something. We actually hand you a noun that looks like some knock, and you evaluate that. So a large portion of my developer time has been figuring out an analysis that lets us go from that to something where we can actually ahead of time name the other arms that we're going to run. And this does two things. One, it keeps your CPU happy. CPUs do not like trees. They do not like branches. They like to go really fast in a straight line. But the other thing that it does is it means you can look up your jets ahead of time. And if you want to know the #1 reason why knock doesn't go as fast as any other programming language on the planet, it's that right now in the current knock implementation, at every call site where there isn't a jet, we are checking the whole table of jets every time. So if we could just not do that, if we could just establish, when you get here, there won't be a jet, just please continue running the knock, that by itself will speed knock up by a lot. But this is another piece that we have to build for the runtime. We have to actually have a knock interpreter, and in Aries there will actually be 2, because writing that code gen is not something I wanted to do in Rust, so I wrote it in Hoon. So I need an interpreter to run my knock compiler to then be able to run all the knock that you guys want to run. You do actually need jets. Jets are not a nice little add-on acceleration. As I mentioned before, if you try to run your Urbit without jets, you will just sit there and spin, and you won't ever get anywhere. The simple basic math functions as implemented in knock are just not algorithmically feasible. So we just wire up some jets. But there's quite a few jets that you need, and you can't just pull them in from var because the memory representation is different. It's a different language. We're writing arrays in Rust. We're not writing it in C. The API that we expect from jets is different. So we had to go rewrite all the jets. And finally, we have to actually be able to talk to the real world. You can do all the computation you want, and if it never has any effect on the real world, if it never makes something show up on your monitor, something play out your speakers, a packet go over the network, okay, great, you can compute. It's very mathematically pretty. But we didn't make Urbit to be mathematically pretty. We want it to be simple, we want it to be elegant, and we want it to work. So, what does working look like in this case? This is booting a fake, well, it's not a fake Zod, it's a fake dev. This is Ares running. Down here, I think it's hiding behind the chairs, but down here, I'm running it with Arvo's verbose flag on. These are events. These are cards being passed through Arvo's move stack. Tell you a little secret, as of like an hour ago. As Amadeo said, Murphy brought all his friends. We'll leave that running because it'll make a little more progress. But this is where we are in this thing. So now that you have an idea what actually goes into, if you want to build an Urbit runtime, this is what you have to do. This is what we've got working. We have a working memory allocator. We have a working knock interpreter. The code generation actually works. There's just not really anything that can run its output fast. I just haven't written that Rust yet. We have a working jet dashboard. It's the same dashboard, takes the same hints that var does. We won't have to change anything in Hoon to be able to run jets. We have a whole bunch of jets. We don't have quite enough of them, it looks like, because we won't get all the way to a dojo prompt this morning. I'm sorry. I really wanted it. I really wanted that for you guys. We have virtualization, which is essentially how Arvo can detect that things running under Arvo crashed. You run a knock interpreter in knock. It's jetted with the real interpreter, and that interpreter can then, without breaking the semantics, tell knock, hey, the knock that you tried to run in me crashed. We have Earth communication. If you look here, there's stuff coming out. This is slogs coming out of Arvo. We are talking to Earth. So what are we still working on? Well, we need persistent memory. We need somewhere to save stuff. That is actively being worked on. It's very close. It's not done to an integratable state yet. The code gen, once it actually has something to run it, which is this bytecode interpreter here, it needs, there are certain optimizations that it needs and other ones which are very simple, which would be very nice. These three things over here, and some cleanup, some integration, there's some jank over here that we don't want users running into. That's what's between us and actually shipping Ares. That's not all, though, because I want you guys to come to Demo Day on Monday. I'll be showing off some more stuff at 3:15. I'm not going to tell you what it is. You have to come find out. So thank you very much, and I'll take questions.
Do you have any kind of timeline?
Yeah, we are aiming to be shipping in the very early part of next year.
What are the, do you have the numbers on performance optimizations we might see with Aries compared to Ver?
I only have like in my head numbers, which I'm very willing to tell people individually, but I'm not going to say off a stage. It should be really fast though.
What does the bytecode interpreter look like for Aries?
Well, it doesn't look like anything yet, because it doesn't exist yet.
In your head, in your head.
Well, so the really fun part of CodeGen to write is something that, so nouns are trees, and there's a really neat paper from like the early 90s that's basically like, if you're going to do CodeGen, do it in reverse, and when you apply this to Knock, a whole bunch of really fun things fall out of it. And so I call this component of CodeGen the linearizer, because it literally just does very similar to what the Ver bytecode interpreter does, but starting from the other direction. It literally just starts from where you return the value and works backwards and emits straight line code. And so a bytecode interpreter literally just looks like a loop over an array that just does whatever the next byte in the array says to do.
Would we later be able to JIT that bytecode?
You could JIT the bytecode. That would be an option. I mean, you could actually JIT Knock. This is one of the things that Truffle Knock was an experiment in a just-in-time runtime for Knock. You could JIT it. My eventual aim is actually just to emit assembly or machine code directly. And the reason for that is JITs are really optimized for the application that I'm running. I'm going to run once. They're optimized for a very ephemeral setting. Like a web page is the usual place we run a JIT. Your Urbit is not like that. If you have an agent on your Urbit, you're gonna invoke that agent over and over and over again. And that code's not going to change until you upgrade the agent. So it's actually worth spending the resources at CodeGen time to really generate good code for it and get the life cycle right. Because this is code that you're not generating code that as soon as you close the web page, you're going to throw away. You're generating code that's going to run on your personal computer for quite a while.
Is there anything you ran into during the development process for this that like surprised you, or something you ran into where it's like, oh, I did not account for this, or I thought this would behave differently?
Oh, all sorts of things. I would say the degree to which things in R, like you expect the math stuff and the bit mashing stuff to rely on jets. I would say I had heard of things like the compiler jets, and had not really hit home for me the degree to which the compiler relies on those, the degree to which things rely on memoization. There's a whole bunch of things that if you just look over Ver, you think of as like nice optimizations that were added in some point that are actually load-bearing. And this talk did not go into all of them. And there's just a whole bunch of pieces that several people have worked I've actually built very little of that myself. Several people who come onto the project have worked very hard to build most of that load-bearing infrastructure that's necessary to get to this demo. And that is, like, the number of those things and where they were has been very surprising to me. In particular, Alex over here, David, Matt, and Neil have all been incredible contributors. Philip isn't officially like paid to work on Aries at all, but has put in a lot of time, both writing stuff for Aries and also helping. All of us are much newer to Urbit than Phil is, and so helping us understand these corner cases, these load-bearing things, this like, okay, this looks trivial, but if you pull it out, the whole thing falls down pieces. And Joe has been incredibly helpful for me to talk through the semantics of Knock, what works and what doesn't for how knock works, how we use knock, how Hoon uses knock.
So there's been some recent criticism about Urbit's performance. And
Yes.
how would you answer some of that criticism that Urbit is not ready for larger applications like a personal computer, and it never will be?
Well, the first part's true. It isn't ready yet. But it never will be is a failure of vision and, quite bluntly, a failure of patience, because this project is ongoing and I haven't been quiet about the progress that we've been making. So I think some of it stems from some technical analyses by some very smart people, and some of it stems from the fact that, like I said, this is the first time that there's been a concerted effort to really try to charge through the runtime barrier all at once, right? Ver is a brilliant piece of software. Urbit wouldn't exist without Ver. But to take the next step and make Urbit performant, it requires a concerted effort to build the kind of runtime that can actually run these applications. And it just hasn't actually been tried before this, as far as I can tell.
Will you summarize the path from the events in the pill all the way to what we saw on the terminal? Just like in a gist, like where does the code gen fit in? Where's the tree walking?
So the code gen is not,
cetera?
the code gen in particular is not running in this demo. But in this demo, basically, we're using Ver's king. It's the executable that has the I/O drivers, parses a pill, puts stuff back on your screen, and Aries is running as a serf, which means it runs knock, it talks to the king, it keeps track of the current state of Arvo. And so when we, let's pull that back up and see what kind of progress it made. It's working on building Arvo right now. That's what it's doing. But it's doing it sans one or two necessary compiler jets, so it's trying very hard. So the king is parsing the pill and then feeding it to the serf as its initial event. And there's a great talk that I think it was Joe and Neil did on YouTube. There's a live stream. I think it's just called the Urbit boot process. You could go search for it. And if you really want to understand in detail how that goes, you should go watch that talk. But in terms of Aries, our initial just tree walking interpreter is running all of this right now, and is and it's literally just being fed from the I/O layer. It's being handed, here, this is the knock you need to run with this subject, and here is the jet state that you need to run. It's really not, that pipeline is very short, but all the stuff underneath the interpreter that's just like, how do you run knock at all? There's been a lot of work put into that.
Does the new runtime help at all towards parallelization?
In one particular way, which is that the memory allocator is very easy to fork off and just have a separate instance of. You still, like, parallelization of trees is actually a hard problem. They feel like, the term in the research world is embarrassing parallelism, because it feels like it should be really easy, right? You've got this data and that data, and they could both be computed, and then you could put the results together afterwards. And it turns out it's actually, with trees, it's actually really hard to get good gains from parallelism. That's not to say we can't do it, but the thing blocking parallelism for knock is not the runtime. The thing blocking parallelism for knock is that first knock has to go fast in a straight line before it's even worth parallelizing it. And secondly, most of the things that you actually probably want to parallelize, you probably want a jet that does SIMD type stuff. There's not enough, there just isn't enough parallelism in something like an Arvo event at the tree layer to really make all the effort worthwhile.
However, could you parallelize things that are outside the event loop, such as cries?
Oh, absolutely. This is one of the first things that I want to do once we actually ship, is build the ability to just concurrently run scries.
Perfect.
Yeah. Any other questions? All right, thank you, everyone.